So today we'll continue our discussion of compiler optimizations and optimizing the performance of a program. So last time we talked about multiple compiler optimizations. So let's see if we can remember the compiler optimizations that we talked about last time. So, okay, so constant propagation.
Constant folding, function inlining.
Okay, so what's the difference between constant propagation and constant folding? Yes?
So for constant propagation, you're just substituting constants for variables that don't change.
Yes.
And then for constant folding, you're evaluating functions or you're evaluating expressions at compile time, and then those become constants.
Yeah. If these expressions are consist of constant operands. Yeah. Yes. So constant folding. And what else?
Common subexpression elimination.
Yeah. Common subexpression elimination.
Prefetching.
Okay. Prefetching.
So what else was there?
So prefetching is one optimization. This optimization obviously requires hardware support, right? Because what we are doing here is, what the compiler does is that it inserts prefetch instructions. So it inserts a prefetch instruction. And in order for the compiler to do this, the hardware must have that, the processor must have a prefetch instruction that allows it allows a program to request the prefetching of a certain memory location, or in fact cache line, beforehand. Okay, so prefetching requires hardware support, but in fact, I did prefetching in the GCC compiler, and it is done at the intermediate level. It's applied to the IR, the intermediate representation. So it's not applied to a low-level representation of the code, because prefetching requires analyzing the program at the intermediate level. It's tightly related to loops. Right? You want to prefetch in loops, because prefetching outside loops is unlikely to be useful. So why is prefetching useful when it's inside the loops? What's the point? What's the idea behind prefetching?
Prefetches data into the cache so it can be used while you run the loop.
Okay, so
it's already in the cache, so it speeds things up.
So how do we do it, within the loop? Why is it closely related to the loop?
If you're doing like a matrix computation, you can fetch. If it's a small matrix, you can fetch it into a cache line. But if it's a large one, then you have to count how many iterations ahead.
So do we just prefetch a whole array? Is the idea to prefetch a whole array and just put it in the cache?
Not the whole array. You prefetch parts of it.
Yeah. So how does it? What do we prefetch? So, and when we are in iteration X, what do we prefetch? So when we are in iteration X, we prefetch something for a future iteration, right?
Right.
And what we prefetch for a future iteration, this calculation depends on two factors. What are the factors? The factors that determine for which iteration should we be prefetching?
How fast the loop executes, and
yeah, exactly. The amount of time needed for one iteration of the loop. And of course, this is going to be a rough estimate. And the other factor
how many iterations ahead you need to prefetch.
Well, that's what we need to calculate. But what is the other factor that we need in order to do this calculation? So I need to know how much work is done inside the loop, how much work each iteration of the loop takes.
Main memory access time.
Yeah, exactly. The example that we gave last time, if it takes 500 cycles to fetch something from main memory to the L1 cache, and each loop takes 100 cycles to execute, then I need to prefetch 5 cycles in advance in order for the data to be available when I need it. If I don't prefetch it early enough, then it's not going to be useful. And by the way, if I prefetch too early, if prefetching happens too early, what can happen?
It can get dumped out of the cache.
Yeah, exactly. You may lose it. If you prefetch it too early, then you may lose it. Okay, so this is prefetching. What are the other optimizations?
Function inlining.
Yeah, inlining.
I think that was the last one we covered.
Function inlining. Yeah, we covered other things.
Well, we covered cost-benefit analysis.
Well, that applies to all optimizations.
Yeah.
And what else?
That optimization scopes.
Yeah, optimization. Well, so now I'm looking for the different optimizations that we have covered.
That's all we covered.
No.
Loop invariant.
Okay, loop interchange.
Oh yeah, that's right. Loop interchange.
And one more.
Loop invariant code motion.
Yeah, loop invariant code motion. Okay, in fact, let's look at this example. So now this is a question. This was an actual question in last semester's final exam. So the question is, identify the optimizations that can be done when we are doing intra-procedural optimization, and the optimizations that we can do when we are doing intra-procedural, when we are doing inter-procedural. So now, remember from last lecture, there is a scope for each optimization. So the scope can be a basic block, or a function, or it can be a whole program. But there are some scopes in between. So between a basic block and a function, the scope could be a region. A region that consists of a subset of the basic blocks in that function. And between a function and the whole program, an optimization may be applied to a subset of the functions, typically to the functions that belong to the same module, to the same source file. So it could be functions in the same, or just call it the module or the source file.
Or class.
Class. Well, once you generate an intermediate representation, you lose all of that, object-oriented programming stuff. All of these high-level constructs. So, once you generate the intermediate representation, once you generate the abstract syntax tree, then you lose your high-level constructs. So you no longer have them, but you can keep them in certain cases. You can keep them, but normally, once the intermediate representation is constructed, we lose the symbolic information and we lose the high-level constructs. So once we construct the intermediate representation, we don't know what the source language was. Okay, and usually there are compilers like GCC, the GCC compiler can compile many different languages, a large number of languages that you have never heard of. So it can compile many programming languages, and it just has one intermediate representation. So once it constructs the intermediate representation, you don't know what the source language is. Anyway, so if we are doing things within the procedure, what are the optimizations that we have here?
Let's see. Intra, we have constant propagation.
Yeah.
Constant folding.
Yeah, well, we have
Constant propagation.
We have constant propagation because this is a constant, and we can propagate the constant to C. So this is, and this is also C. So we have, we can replace this with 5. So this is constant propagation. So we can say, okay, constant propagation, propagate C equals 5. So substitute 5 for every C. Now we are passing C to this function. Can we propagate it across functions? No, we can propagate it when we are doing inter-procedural analysis. But when we are doing intra-procedural, we cannot. So intra-procedural means that the optimizer looks at one function at a time. When it looks at one function, it doesn't see other functions. It doesn't move. It doesn't do anything across functions. So this is what intra-procedural. So this is within the procedure. This is across procedures. Okay. So this is one optimization. What else?
Now we've got some common subexpressions there, A minus.
Yeah, exactly. So we have A minus B. This is common sub-expression. So this is number 2. We have common sub-expression elimination, A minus B. So we can do, T equals A minus B and D equals T, or you can use, depending on how you implement this, and then F equals E plus T plus C. Plus 5. Okay, so these are the optimizations that I can see within this function. Within the other function, so what do we have?
Constant folding.
Yeah, we have just constant folding. So we have Y constant folding. Y equals 6 times 4, 24.
26.
Plus 2, 26. And we can, we can assume that constant propagation is done after constant folding, followed by constant propagation. And then we'll have if x is greater than 26, etc. Okay, so this is what we can do within each function. So remember that intra-procedural, and this is, by the way, this is the most common optimization. So compilers normally do intra-procedural analysis and inter-procedural analysis. Not all compilers implement it. because it's complex. So I remember at some point GCC did not have, back in maybe 10 years ago, I think, 10 years ago or 12 years ago, GCC did not have inter-procedural analysis and inter-procedural optimizations. Now it does. So compilers evolve, by the way. So a compiler evolves. They add more optimizations over time. Okay. Inter-procedural analysis is done usually if you enable it, and if it's implemented in the compiler that you are using. Now, assuming that we have inter-procedural analysis, what can we do here?
We could inline function G.
Yeah. Okay. So the function, if you inline the function G. Okay. So inlining function G, we'll get E equals G of C. So this is going to be, in fact, E will get the return value of G. So here we have y equals 26, and if x is greater than, now what is x?
5.
Yeah, x is 5. So if 5 is greater than 26, return 1, else return 2. So when you inline, there is no return, in fact. We're just showing this intermediate step. So when you are inlining a function, there is no return. What this will get translated to is y equals, E equals the return value, and the return value in this case is what?
2.
Is 2. So this function call will reduce to E equals 2. Okay, yes?
So when you do inlining, you evaluate everything inside the function before assigning to...
Yeah, so normally inlining, you put everything, but then after you, in fact, the inlining here would be not return 1. If 5 is greater than 26, E equals 1, else E equals 2. Because E is receiving the return value of the function, and with inlining there is no return. Return doesn't make sense when you inline. You are just copying the body of the function. So instead of returning, you just assign this value to the variable that will receive the return value. The variable that receives the return value here is E. So instead of returning, you assign to the variable that receives the return value. And because 5 is not greater than 26, E it will be equal to 2.
So couldn't we have unreachable code elimination from the E minus 1? In fact, could we get rid of the conditional altogether since it's always going to be false?
Yeah, so we did it. So this is an intermediate step here. By the way, it's, this, I should note that because we are studying optimizations conceptually, we are not studying specific algorithms. So this is kind of fuzzy because it's not clear what will actually get done. What will actually get done will depend on the algorithms. So this part of the course is kind of fuzzy relative to the other parts where we studied specific algorithms. Here, since we are not studying specific algorithms, it's the answers are not well defined, I guess, because it all depends on which algorithm. So an algorithm may or may not capture certain optimizations that we hope it will capture. So whether the optimization will capture what, in this case, whether the optimization will be smart enough to capture all what we wanted to capture and set E to 2 that will depend on the specific algorithm. So the algorithm may miss this, and it may still keep the if-else, depending on what is being implemented. So we'll have to, here, when you are asked a question like this, just give all the optimizations that you think can be done. So in fact, a question like this can be answered more wishfully, compared to questions about specific algorithms. So when there is a question about a specific algorithm, it should be answered based on what that algorithm will do, whether it will be smart enough to capture all the optimizations or to take advantage of all the optimization opportunities that are there or not. If there's a specific algorithm, the answer is well defined. But if there is no specific algorithm, then just point out all the possible optimizations. But at least we need to distinguish between intra-procedural and inter-procedural. At least we want to understand that unless the compiler does inter-procedural analysis, it will not be able to do something like this. It can do these things, but it will not be able to do something like this that is across functions. So this is an important concept. In fact, this is the main concept in this question. The distinction between intra-procedural and inter-procedural. Okay, so here we will hope that the optimization will be able to do this. And in fact, this is when we reduce all of this to e equals 2, we have eliminated one of the branches. We have eliminated the branch. We have eliminated one of the basic blocks. This whole basic block, we have eliminated it because it's unreachable. Okay. So do you see anything else?
Well, the whole thing doesn't have any side effects and it doesn't return anything. So can we just not run any of this?
Okay. So just erase it. So this is the eraser optimization. Okay. Well, yeah. Well, you are right. Now, it's okay. Yeah. So this is a function that, in fact, is not accessing any global variables, and it's only accessing local variables, and it's not returning anything. So you are right about this. It's but that wasn't intended. Okay.
Can we actually put that on the example and get something like that? Eraser optimism.
Yeah.
Elimination.
Well, yeah. So the compilers do eliminate code, do eliminate dead code, and in fact all of this will, if it's not used, then it will be dead code. So if the whole function is not returning anything, and this shouldn't be a void function. Yeah, a void function that doesn't modify global variables is a function that will not do anything. So you are right about this, but this was not intended. So you can't say this. You will get extra credit probably if you do this in the test. Okay. So anything else? So after we do e equals 2, we can do constant propagation, right?
And then constant folding again.
Yeah. So in constant propagation and constant folding, you can do multiple passes because constant propagation can enable constant folding, and constant folding can enable constant propagation. So you can do multiple passes, but a real compiler will not do an infinite number of passes. It's common for a compiler to apply a pass multiple times, between optimizations, especially things like dead code elimination. The compiler can do it multiple times, after different optimizations, because optimizations can result in dead code, and then we need some cleanup stage to clean up some of the dead code that may get generated in one by after applying one optimization